Hello everyone, I am Ashmita Sutradhar from Electrical Engineering Department, NIT Silchar. Today we are going to learn about the initial concepts of the chapter Chemical Bonding and Molecular Structure. When we talk about chemical bonding, there are various types of bonding like covalent bond, ionic bond, metallic bond, coordinate covalent bond, etc. So today we are going to start with ionic bond. Now, ionic bond is also called electrovalent bond. In ionic bond, we see a force of attraction which is called electrostatic force of attraction, and we see complete transfer of electrons between metal and non-metal. This electrostatic force of attraction can be given as F equals to K Q1 Q2 by R square, which is a very strong type of attraction. Now we are going to take an example of a metal and non-metal. Let us take an example of a metal, sodium, given as Na, and its atomic number is 11, which is denoted by 2.8.1. As the octet rule says, as per the octet rule, it loses one electron and becomes Na plus and electron minus, and it becomes 2.8. Octet achieved. Now we are gonna consider a non-metal, Cl, chlorine, which is given by 2.8.7, and it acquires this electron and it becomes Cl minus. Both this Na and Cl are in gaseous form, which is a very unstable form. Thus, this Na plus and Cl minus forms an ionic bond forming NaCl solid, which is a very stable form. Since electrostatic force of attraction is very strong, and this Cl minus and Na plus are in gaseous form, which is unstable form, they form a component in solid state named as NaCl and achieves a stable form. Now we are going to come to the next topic, which is Lewis-Dot structure. This topic is very simple and important, as we have taken the previous example is of NaCl. So I am going to start with the example of NaCl in Lewis-Dot structure. Here Na has an extra electron in the outer shell, which Cl, which has 1, 2, 3, 4, 5, 6 and 7. It achieves the extra electron from the Na and becomes NaCl. This can also be denoted as Na plus Cl minus 1, 2, 3, 4, 5, and it is denoted as cross, as this electron is achieved from the Na. This is basically, and we can also show the electrostatic force between them. This is the Lewis-Dot structure of NaCl. Let us take another example of MgCl2. MgCl2. Here, Mg is 2.8.2. It has two extra electrons. gives up the 2 extra electrons and becomes Mg2 plus in gaseous form plus 2 electron minus. And the 2Cl achieves the 2 electron minus to become 2Cl minus in gaseous. So this can be denoted in the Lewis-Strauss structure as, I am using this one, as Mg 2 plus Cl 1, 2, 3, 4, 5, 6, 7 and 1 extra electron from Mg, and the other Cl is 1, 2, 3, 4, 5, 6, 7 and other extra electron from Mg. This is the Lewis-Strauss structure of MgCl2. It can also be given as Mg Cl 1, 2, 3, 4, 5, 6, Cl 1, 2, 3, 4, 5, 6, 7, this to here making it 8 and this to here making it 8, achieving the octet group. With this we come to the end of Lewis-Strauss structure, and next we are going to start with electrovalency. Now, what is electrovalency? The definition of electrovalency is basically the number of electrons lost or gained. And the most important topic or the most important point of electrovalency is it can never be negative. Let us see an example. Like we'll take the group 1 elements like lithium, sodium, potassium, electrovalence. The electrovalency of group 1 elements is 1. Group 2 elements. The electrovalency is 2. Group 3 to group 12 elements are B block elements. Thus, they have unstable electrovalency. So we are not denoting it here, because we can take the example of iron, which shows electrovalency plus 2, plus 3. So it has variable electrovalency, so we are not considering it here. We are going to start from group 13. Aluminium, and the electrovalency is 3. Group 14, carbon. This group 14 elements don't form ionic bond. They share electrons. They form covalent bond. That they don't have any electrovalency. Now we are going to start with group 15. NPAS has electrovalency 3. Group 16, oxygen, has electrovalency 2. Here they gain 2 electrons, but the valency is not negative. We consider it as positive 2. Group 17, F, Cl, Br, electrovalency is 1. Here, with this, we come to the end of the topic electrovalency. Next, we are going to ask ourselves a question and see which component is more ionic? We are going to see the ionic characteristics of the components. Let us consider a question. NaF, NaCl, NaBr and NaI. In this, which is the more ionic component? So how do we derive this? Here the metallic component is the same, but the non-metal is different. So we have to note that down the group FCl, Br, I, down the group the non-metallic character decreases and the metallic character is the vice versa, increases. So now the question is, what makes a component more ionic? Either the metallic character or the non-metallic character has to be increased. Here we can see FClBr I. Down the group the non-metallic character increases. Thus NaF is more ionic than NaCl, then NaBr, then NaI. This is the trend that it follows. We are going to take another question. Let us consider the next question is LiCl, NaCl, KCl and RbCl. Here we can see the non-metal is the same, but the metals are different. So how do we determine the ionic character? As I said previously, that the metallic character down the group increases. So here we can see Li, Na, K, Rb. Down the group, metallic character increases. So the most, the component that the element that has the most ionic character or metallic character is Rb, K, then Na, then Li. So the trend would be RbCl, KCl, NaCl and LiCl. RbCl is the most ionic and NiCl is the least ionic. So with this we come to the end of today's class and we are gonna see what are the topics that we covered. We covered ionic bond, its examples with NaCl, Lewis-Dot structure, then electrovalency and the ionic character and determination of the ionic character. Thank you, that's it.